Welcome to the next session on Learn Before You Solve. So, in this video, we are going to see about the CV characteristics of MOS transistor, and the second part of the video will cover about the problem which we are going to discuss on CV characteristics of MOS transistor. To have a look into the different capacitances in a MOS transistor, first let us realize how this MOS can be considered as a parallel plate capacitor. So, we can see that MOS is nothing but a metal oxide semiconductor device wherein we have this gate metal as the metal portion, and we have the silicon dioxide layer which is going to act as a dielectric medium, and we have this semiconductor here which is partially conducting, and usually the parallel plate capacitor which we are going to represent in MOS is based on the formation of channel. So, the channel is nothing but it is a rich of electrons where the channel is formed when the gate is induced with a particular amount of applied voltage. When the applied gate voltage is greater than VTH, which means the threshold voltage, when VGS is greater than the threshold voltage, and when we apply the drain to source voltage as greater than 0, a small positive voltage when we apply, and when this VDS is going to be less than VD sat, we call this VD sat as VGS minus VT, where that is the maximum saturation voltage until which the device will behave as a linear MOS transistor. And here we can see that at this condition there will be a formation of channel here. This channel will have the electrons because the applied voltage is a positive voltage which will try to repel the majority holes which are present in the p-type substrate, and hence the minority carriers which are electrons in the p-type substrate get attracted towards the positive gate to source voltage, and hence we have an inversion layer which forms as a channel between this source and the drain region. This layer of inversion being a conductive layer, and the metal, gate metal which we have, that is also a conducting layer, and in between the two parallel plate conducting plates we have a dielectric medium which is nothing but our insulator layer, SiO2 layer, and hence this can be viewed as a parallel plate capacitor. So, similar to this is we have a metal, and here we have the oxide layer, and then we have the channel here. So, that is also a conductive region because we have full of electrons. So, this we can interpret this MOS transistor as a capacitor. So, taking that into consideration, we will first look into the general parallel plate capacitance formula, where we write the capacitance as epsilon A by D, where epsilon is the permittivity of what material that we are using, and D is the thickness of that particular capacitor, and A is equal to area. Keeping this in mind, the first capacitance that we are going to find out is the gate capacitance, that is represented as Cg equal to Cox into WL, where Cox is nothing but epsilon ox by Tox. Epsilon ox is the oxide permittivity, where here it is nothing but epsilon ox is our 3.9 epsilon because we have used here the silicon dioxide, and epsilon naught is the permittivity of the free space, which is 8.854 into 10 to the power minus 14 farad per centimeter. So, with that into mind, we have obtained what is Cox. So, it is epsilon ox by Tox, where Tox is the thickness of the oxide layer, and here you can see that we have epsilon by D. So, which means we have attained this. Epsilon by D is equivalent to epsilon ox by Tox, and here we have rewritten this format as in terms of Cox, and then left out thing is nothing but the area term. Area is nothing but length into breadth, where here we are concentrating on the channel length, or we call it as the gate length, which is denoted in terms of L, and then we have the width of the channel which is going to extend it like this. So that width is given as W. So hence area is nothing but L into W. Hence the gate capacitance we are writing it in terms of Cg equal to Cox into L into W. The next capacitor is nothing but gate to channel capacitance, where gate to channel capacitance, it is behaving again like a parallel plate capacitor. So here what we can do is, this channel will have the influence of both source and the drain, where channel is formed in a way that it is exactly halfway through source and halfway from your drain. So therefore the gate to channel capacitance can be written as gate to source capacitance, influence of source, and influence of drain will be there. So gate to drain capacitance. So the summation of gate to source capacitance and gate to drain capacitance is nothing but the gate to channel capacitance, with the capacitance that is formed between the gate and the channel. Fine. So gate to channel capacitance, we have, it is nothing but the gate capacitance. We know that it is Cox into WL, and this gate to channel, this channel is formed only when we apply VGS is greater than VTH and VDS is greater than 0, and only at the linear region we have this channel formation. Unless otherwise the linear region is formed, this gate to channel capacitance will remain as 0 in the cutoff region, wherein we don't have any formation of channel. So that we will see separately in the next slide. Here what you have to understand is, gate to channel capacitance is the sum of gate to source and gate to drain capacitance. So once we know gate to channel capacitance as Cox into WL, and gate to source and drain capacitance will be exactly half of the gate to channel capacitance. So that is why CGS and CGD are written as Cox WL by 2. And the other capacitance that we have to concentrate is the gate to body capacitance. So far we have discussed about CGC, CGS, CGD, and the next thing is gate to body. So we are connecting each and every terminal with the gate to channel, gate to source, gate to drain, gate to bulk, since we have 4 terminals, right? So bulk, or you call that as a body, or you call that as a substrate terminal. So when we have to write the capacitance for gate to bulk, which means in the cutoff region you don't have any formation of channel, so it is again equivalent to the gate capacitance Cox into WL. So therefore gate to body capacitance in the cutoff region, when there is no formation of channel, you will have only gate oxide layer and then the substrate. The substrate is also a semiconducting layer, so therefore that is also again, it is like 2 parallel plates. In between that you have a insulation layer. So therefore again that CGB is also equivalent to CG, gate capacitance. So therefore it is Cox into WL. Channel is fully conducting and body is nothing but substrate, which is a semiconducting substrate. So therefore it is partially conducting. So therefore gate, oxide and semiconduction is there, and that is also related again with the gate capacitance. So therefore CGB in the cutoff region, it is Cox into WL. So here you can just write it down that it is only for cutoff region. For other regions we will just look into that, what is going to happen. Okay. Now concentrating in the capacitance during cutoff region is, during cutoff region the condition for cutoff to occur in a MOS transistor is that VGS is less than VTH. VGS, the gate to source voltage, is less than VTH, which means it is in cutoff region, and therefore here we will just look into the channel formation, where the channel formation here it is nil. So therefore no channel is formed here. So this thing we need to keep it in mind. For in regards to CV characteristics, we are not going to discuss about the drain current here. So with regards to CV characteristics, we will look into what kind of, whether it is channel is formed, whether it is channel is linear, or whether it is pinched off. So that we are going to discuss, and based on that we will write the capacitance values. Now for CGB, as we have discussed in the previous slide, it was in cutoff region, it is going to behave like a gate, and you have an oxide layer, and then this is going to be a substrate, P-type substrate. It is again a semiconducting layer. So therefore this will again behave like a capacitor, which is equivalent to your gate capacitance Cox into WL. And now coming for the gate to channel capacitance, this capacitance we are going to look in, and we know that gate to channel capacitance is the sum of gate to source capacitance and gate to drain capacitance, right. So now we need to know what is gate to channel capacitance. Gate to channel capacitance, here in cutoff region we don't have any formation of channel, so this we should remember. So therefore when there is no formation of channel, CGC is gate with respect to channel, then there is no formation of channel, CGC is going to be 0. When CGC is 0 in cutoff region, CGS is also 0 and CGD is also 0. Now talking about the capacitance in linear region, here we can visualize the formation of channel between source and drain. Here when is the channel is going to form? With the condition that VGS is greater than VTH. So these are going to be the conditions for linear region, and my VDS is greater than 0 and it is less than VDSAT, and in the previous slide I have written what is VDSAT. VDSAT is the maximum voltage until which the drain current will behave linearly. So here talking about the channel, the formation of channel will be, you will have an inversion layer formation that is formed after a depletion layer. Of course, an inversion layer, here there is a formation of channel with rich flow of electrons here, and when you are applying a positive voltage, the electrons will move from source to drain, and hence there will be current induced, that current will increase linearly with respect to your VGS. Now talking about, we are interested about calculating the different capacitances in a MOS transistor. So when we talk about gate to body capacitance, here we have a formation of channel. So here we are no more going to concentrate on gate to body capacitance, so that will become 0 in linear region. And gate to source channel capacitance, it is going to be CGS plus CGD, and here you can see that CGC is nothing but you have gate, oxide layer is there, and then you have this channel which is behaving like two parallel plates between which you have a oxide layer. So therefore this is exactly equivalent to CG, which is the gate capacitance, which we have derived in the previous slide, which is Cox into W into L. So we know that it is combination of both CGS and CGD. So therefore CGS is going to be 1 by 2, exactly half of gate to channel capacitance, Cox into WL, and similarly gate to drain is also going to be Cox into WL, because exactly at the half of the way we have the influence of source and we have the influence of drain. So each thing we are going to consider as 1 by 2 of Cox WL and 1 by 2 Cox WL. Now coming for the third region of operation of MOS transistor, here we are going to talk about the saturation region. So here the condition for MOS transistor to enter into saturation is VGS greater than VTH and VDS is greater than VDSAT. So above this greater than or equal to you can have. Above this voltage, the channel is going to behave like a pinched off channel. So the channel is said to be pinched off here, wherein you will have the extension of the drain depletion region further downwards, extending the p-type substrate. So therefore most of the influence for the capacitance will be from the source and not from the drain, and therefore here you can see that it is exactly more in terms of source side than in terms of drain side. So therefore here instead of splitting the gate to channel capacitance as exactly half of the influence of source and drain, instead of that, here we consider this is going to be 2 by 3rd portion of the total area that is occupied, and here you don't have any influence because it is completely going to form a drain depletion region when you try to increase your VDS. So therefore here this side it is going to be 0. So therefore, we will first write down what is gate to source capacitance. It is going to be 2/3 times of Cox into WL, because here you have the channel. So this you can write it as metal oxide, conducting layer is there, and it is almost 2/3 portion. So 2/3 Cox WL, and drain has no influence here. So therefore, this is going to be 0, and addition of both gate to source and gate to drain is going to give us the gate to channel capacitance. So this will be again 2/3 Cox into WL. And gate to body capacitance, here we do not concentrate on body because we have an in between formation of channel which is pinched off. So gate to body capacitance is going to be 0. This is a summary of capacitance in 3 different regions of operation of MOS transistor. So whatever I have derived in the last 3 slides is shown in the tabulation format. Now here we are going to concentrate on overlap capacitances. So far we have seen capacitances that are related with gate. So we have discussed about CGB, CGC, CGS and CGD in 3 different regions of operations of MOS transistor. And the second thing that we are going to concentrate is the 2 special components of CGS and CGD, which are caused by the lateral diffusion under the gate and the thin oxide. So here you can see that there is an overlap between this gate and the source. So this portion you have an overlap between your source and the gate portion is overlapping. So this you call it as CGS overlap, where CGS overlap we are going to define, and one more overlap region is there with regards to drain side, because source and drain both are symmetrical, right? So when they are symmetrical, here also you can see that there is a overlap region between gate and drain. So here also there will be formation of capacitance. So that capacitance is going to be CGD, gate to drain overlap capacitance, and this is going to be, here you can see that this is gate region and you have an oxide layer, and the overlap region is with source, which is again of N type, right? And similarly this side also gate oxide portion is there, and then you have an N type which is again rich of electrons. It is going to be conductor. So there is a formation of capacitance. So this you can write after defining what is the overlap length. Here the overlap length is going to be defined as LD, or you call that as a diffusion length. LD is lateral diffusion length. Lateral diffusion length, which is on both the sides of source and drain. So this also we will be marking as LD. So now easily you can write down the formula, which is Cox, that we know W into L is going to be LD. So that is the same case with respect to CGD also. So these are going to be the 2 overlap capacitances which are bias independent. Now we will move on for the last portion of capacitances, which are depletion or diffusion capacitances of MOS transistor. We have the diffusion capacitance model here, where the diffusion or the depletion capacitance, we call it sometimes, is basically based on the depletion regions that are surrounding the source and the drain side. The formation of depletion region is a very usual procedure until we apply a positive gate voltage. This depletion region will try to continue. Only after applying a positive gate voltage, the depletion regions will try to break out, and the electrons, which are minority electrons in the p-type substrate, will get attracted on the surface below this metal oxide layer, will get inverted here, and there will be formation of channel. So until that, this source depletion region will be there and drain depletion region will be there. And here today we are going to concentrate on CSB, which is the source to bulk substrate. The source to bulk is nothing but the junction, where the junction is, here the bulk is p-type substrate and the source is n-type, and this depletion region is nothing but the junction which is between the source and the substrate, or you call it as a bulk. Similarly, we have the formation of this junction here with this drain and the substrate regions. So, now we will concentrate on calculating what is CSB, and wherever we find this S, we are going to replace it with D when we calculate CDB, because source and drain are symmetrical in nature. So, whatever length we are going to consider for source will be retained the same for drain to bulk calculation also. The source to bulk capacitance is given here, which is AS is going to denote the area with which this source to bulk is going to occupy, and CJBS is the junction capacitance between the bulk and the bottom of source. So, here you have this rectangle or a square you can even consider. So, what we are going to consider is, we have a certain area for this square, which means the source region, and we have 4 sides with which we can calculate the perimeter also, and we have a junction which is formed between the source and the substrate, and that junction capacitance we have taken in terms of the bottom of source and also in terms of the side walls of the source. So, these two you call it as side walls of source, side walls of drain, and this is bottom of drain and this is bottom of the source. And here we are going to consider area into junction capacitance between the bulk and the bottom of the source, and then what we are going to do is find out the perimeter, and then CJBSSW. CJBS is junction capacitance between bulk and bottom, and CJBSSW, where SW is always representing the side walls. So, we will calculate the perimeter, because perimeter will only calculate all these 4 regions, all these 4 sides. So, that into your junction capacitance between your bulk and side walls of the source, and this area is given as length into width. Here the length of this bottom of the source is taken as D, capital D, and width is going to be the same W that we are going, because it is going to extend like this. So, it is always W. And for perimeter calculation, this is looking like a square or a rectangle, whatever we want we can consider. Perimeter is always the sum of all the 4 sides. Here we have the 4th side is the top of the source. So, it is D plus D, and we have to add the side walls length also. So, this side walls you will have it as in terms of width. So, that is represented as W. So, you have 2D plus 2W. When you write 2 in common, we have D plus W. Okay. This is when you consider both the side walls. Here the one which I have highlighted in pink color is the side wall which is facing the channel. Suppose if you have the formation of channel, this side wall is going to face the channel, and this side wall is the only wall which is in contact with the gate. So, this is partially in contact with gate. So, therefore, sometimes we will try to neglect this side wall or add this side wall separately, the calculation of this side wall, because this will induce some other capacitance also. So, therefore, here when you are calculating the perimeter, sometimes we take it as the top and bottom of the source side and one side wall which has no disturbance, like this pink color side wall which is facing the channel and which is also partially in contact with the gate. The explanations for CJBS SW is given here, where junction capacitance you can write it in terms of Cj into 1 plus VSB by psi naught power minus Mj, where Cj is the junction capacitance at 0 bias. When you don't have any biasing, we write it as Cj, and 1 plus VSB, where VSB is nothing but the source to bulk voltage, and psi naught is the built-in potential, which we write it in normal as Vt ln Na Nd by Ni square. Vt is the thermal voltage, Kt by Q, and Na is acceptor doping concentration, Nd is donor doping concentration, and Ni is intrinsic silicon concentration or whatever base we take. And Mj is your junction grading coefficient, which will most probably vary from 0.5 to 0.33. And the next thing is, we are going to write down what is this side wall capacitance. CJBSSW is going to be CJSW, the junction capacitance of the side wall, and side wall capacitance in common to gate and channel. So this is the sidewall which is not in common to gate or with channel. This is not facing the channel. So this sidewall we calculate separately because of the common connection between the gate and the channel. We always do this separately. That is why sometimes the perimeter is taken as 2D plus W, considering only this sidewall capacitor, considering only this sidewall width. This sidewall width we will do it separately, we will do the perimeter calculation separately, and this sidewall capacitance which is going to be in common to gate and the channel. And at 0 bias, all this CJBS, which is the junction capacitance between your bulk and bottom of the source, is going to be equal to Cj at 0 bias, and CJBSSW is your sidewall capacitance, that is going to be equal to CJSW at 0 bias, because when you consider this 0 bias between your source and bulk, so this term will become 0 and CJSW into 1 will be there. So therefore we have this CJBSSWG equal to CJSWG at 0 bias, and all these things are going to be applicable for the drain to bulk capacitance also because of the symmetrical structure. With the help of these formulas and the CV characteristics which we have understood for 3 different regions of operation of MOS transistor, and we have also understood what is overlap capacitance, and we have also seen the diffusion capacitance model where we have exclusively concentrated on the sidewall capacitance and the capacitance of drain to bulk and source to bulk regions. So with the help of these formulas, we will try to solve one important problem in the second part of the video. So thank you all for watching this video through Electronics Insight channel.